Hello, Dan here from howtomechatronics.com, and in this video I will show you how I built this beast of an RC tank or a radio-controlled track vehicle featuring clean, all-black design, some cool LED lighting and a dual-speed gearbox. That's right, I specifically designed a gearbox for this tank so I can choose a lower or higher gear depending on the terrain or the application that is used for, and so get either higher torque or higher speed. If you follow me, you might know that some time ago I already built a 3D printed RC tank, which was cool but a bit underpowered. That's why now for this build I am using 200 watts DC motor for each track, and in combination with this gearbox, the tank has plenty of power to conquer any terrain or to have some fun doing burnouts or donuts with it. Yep, it's super fun doing burnouts with it. Talking about having fun, I installed an addressable LED strip for the lights, which gives endless possibilities for creating stunning light effects. For this video, I made a police lights strobe effect, which is so cool driving around with it, especially at night. As for the suspension, on each side the tank is supported on 3 coil springs and shock absorbers, with 2 road wheels for each of them. That allows the vehicle to run smoothly on uneven terrain and climb obstacles while maintaining good contact surface between the tracks and the terrain. Of course, everything is 3D printed and the 3D files are available for downloading, so you can build one on your own. For controlling the tank, I am using a cheap commercial RC transmitter which sends commands to it. At the tank there is a suitable RC receiver which receives the commands and sends them to a microcontroller. The brain of this platform is an Atmega 2560 microcontroller based board, and for easily connecting everything together, I made a custom PCB which can be simply attached on top of the board. Nevertheless, now buckle up as I will walk you through the entire process of building this RC tank, starting from the design, 3D printing, assembling and connecting the electronics components to programming the microcontroller. I designed this RC tank using Onshape, which is also the sponsor of this video. Onshape is a professional grade cloud native 3D CAD and PDM system that I use for my projects. It is browser based, which means I can log in on any device, I don't need an expensive computer, it never crashes and I never lose my work. It records every action I take and allows for infinite restore. I can collaborate in real time with others on the same design. It has a PDM with branching and merging. Onshape also has some great other tools like FEA and photorealistic rendering as well. Onshape also just announced that they will be offering a plan for US government contractors that require regulatory compliance like ITAR and EAR. I highly recommend that mechanical engineers and product designers check out Onshape. You and your company can use Onshape Professional for free up to 6 months at onshape.pro/howtomechatronics. Check the links in the description. Back to topic, now let me explain how I came up with this tank design. The initial input parameters for the design were the DC motors, or their dimensions, and the RPM. These motors are quite bulky and have 3000 RPM. That's too high RPM for this tank, so therefore I designed this gearbox, which reduces the speed to 2 different values. This gearbox works just like a manual transmission in a car works. There is a gear shifter which, instead of moving it by hand, here it is moved with the help of a servo motor, and it can choose which of the 2 output gear sets will be engaged as a final output. The gearbox initial reduction ratio is 1.88 to 1, which is fixed, and then we can choose either the low gear, which has additional reduction of 2.76 to 1, or the high gear, which has 1 to 1 ratio. So in the lower gear the total reduction is about 2.5, or that's around 570 RPM, and in the higher gear just 1.88 speed reduction, or that's around 1600 RPM. We will see more details how the gearbox work a bit later in the video when we will assemble it. The next input parameter for the tank design were the RC shock absorbers that I got. They have a length of 70 mm when extended with 15 mm travel. I wanted to get a bit greater vertical travel distance for the road wheels, So I positioned them in this configuration and got a vertical travel distance of around 22 mm. In addition to that, as this is a bogie system where a pair of wheels are attached to that moving axis, the wheels can rotate around that axis and so they can make additional vertical travel. Obviously that will provide smoother ride and better contact between the track and the surface underneath. If we take a closer look at the front road wheels, we can notice that they are connected with the idler wheel on the front to provide dynamic tension of the track. When the front road wheels go up, the track circumference gets smaller and so the tension loosens. With this setup, when that happens, the idler wheel is pushed forward to tension the track. With this connection, we can also tension the track statically by adjusting this bolt and distance nut. At the back side we have the sprocket, which is composed of 3 parts. It has a shaft coupler and left and right section of the sprocket connected all together with 3 M3 bolts. The key dimension here on the sprocket is the pitch, because it must match with the pitch of the track. The pitch is 11 mm here, and I chose the sprocket to have 20 teeth, which gave me a pitch diameter of the sprocket of around 69 mm. The idea for the size of the sprocket was to be big enough so that the track stay out of the tank body. The 11 mm pitch was actually defined by the design of the track link. My goal for the track link was to be as compact as possible and to be connectable with the next link with just one additional part or pin, while being strong enough to be made with a 3D printer. On top of that, when 3D printing, I wanted to avoid any use of support material for the part, which I actually managed to achieve with this design. For connecting the track links to each other, I plan to use pins with 2 mm diameter, so I dimensioned one side to be 2.1 mm to get tight fit and the other side 2.4 mm to get loose fit so that the track links can rotate freely. The sprocket teeth engage with the track links at the outer cylinder shape. The track link cylinder has 4.4 mm radius, while the sprocket has 4.9 mm radius, in order to have a loose fit to work properly. The main body, where everything is connected, had to be big enough to fit the 2 gearboxes and of course to have space for the electronics and the battery. All of this resulted the tank overall dimensions to be 547 by 397 mm. That's fairly big, bigger than the usual 3D printer's bed, so therefore I divided the big parts into 2 sections, so we can print them on a 300 mm bed 3D printer. Please note that if you want to print it on a smaller 3D printer with 220 mm print bed, the model has to be divided into 4 sections. I will also provide that version in the 3D files. For assembling the tank, we need various M3 and M4 bolts and nuts, as well as some threaded inserts and bearings. You can find a complete list of all the components needed for this project on the website article. Of course, you can also find the 3D model and the STL files needed for 3D printing. The link is in the video description. I used my Creality Ender 3 V3 Plus 3D printer for printing most of the parts for this tank. When 3D printing, it's important to use the horizontal expansion feature, or now in the new Creality print slicer that I use, it's called XY contour compensation. If we leave these settings by default, the print's outer dimensions as well as the holes are usually smaller than the original model, and we might have problems assembling them. In the Creality print slicer, I used a value of -0.07 for the XY contour compensation and +0.07 for the XY hole compensation feature. Of course, you should do some test prints to see what values will give you the best results on your 3D printer. For 3D printing the track links, I used rafts as build plate adhesion because their base contact surface with the 3D printer plate is a bit small and might not stick well if the bed adhesion on your 3D printer is not good enough. The Creality Ender 3 V3 Plus has a build plate of 300 by 300 mm, so I could print the main body of the tank in 2 sections. Even in 2 sections, the prints are quite big and push the 3D printer to its limit. But the Creality Ender 3 V3 Plus managed to handle it and did a great job printing these big parts. I can highly recommend this 3D printer to anyone looking for a large volume and fast 3D printer. It's a Corax Z 3D printer that can reach speeds of up to 600 mm per second, and with its sturdy frame, it provides really good printing quality. Shout out to Creality for providing me this 3D printer. You can check out the Ender 3 V3 Plus on the Creality web store. The links are in the description of the video. Alright, so here are all of the 3D printed parts, so we can start assembling the tank. To be honest, there is so much 3D printing. It takes like several days to print everything, and not just time, but we also need several spools of filament. For the track links alone, because we need 214 track links total, we need around 500 grams of filament and around 30 hours of 3D printing. The main body of the tank needs around 1 kilogram of filament. If divided into two sections like here, 500 grams for each and around 12 to 18 hours for each section. Also, many of the parts need to be 3D printed with support, so we need to spend some time cleaning. Anyway, I started the assembly by connecting the two sections of the main body together. For that purpose, we need some 25 mm long M3 bolts and nuts. Most of the time I use lock nuts or prevailing torque nuts to be sure they won't loosen easily. I used 12 bolts and nuts for connecting the two sections, which makes the main body rock solid. You can notice though, there is a small gap at the bottom contact point, and that's due to warping of the parts when 3D printing. Warping is an issue that occurs when 3D printing large parts, and it was even worse when I tried printing the parts horizontally. It was easier to print the parts horizontally, but I had to reprint them vertically positioned because of the warping problem. Once we have the main body ready, we can move on with assembling the suspension of the tank. It is based on this RC shock absorber, which has 70 mm length with 15 mm travel. Here's how the suspension setup should look like, but it's better to pre-assemble it on site and then attach it to the main body. So first I'm connecting the two links that form the bogie mechanism. The upper link accommodates a bearing with 4 mm inner and 9 mm outer diameter. Then we slide it into the road wheel link and we connect them together with an M4 bolt and a nut. At the back side of this link there is a slot to accommodate the nut, and when fastened with the bolt they should stay flush with the surface of the link. That's very important so they won't interfere with the main body when attached to it later on. Next we can attach the road wheels in place. For that purpose we will need two bearings with 30 mm outer and 4 mm inner diameter on each side of the road wheels, and an M4 bolt with 40 mm length. Though in between the two bearings we should insert a distance ring, just slightly longer than the opening of the road wheels between the two bearings, so that when we fasten the bolt, the inner parts of the two bearings will support to each other. In this way we will avoid introducing axial forces to the bearings, and so we can tighten the road wheels firmer and still the wheels will be able to rotate freely. In between the road wheel and the link we should also insert a washer. We repeat this process for the other road wheel, and then we install the shock absorber to the upper link with the help of an M3 bolt and a nut. This bolt is 16 mm long, and also, as previously stated, when tightened it should stay flush with the surface of the link. Now we can attach this sub-assembly to the main body of the tank. For that purpose, first we need to attach this bracket with the help of two 25 mm long M3 bolts. This bracket will serve two purposes: to attach the shock absorber to it, as well as to attach the track support wheels to it a bit later. Next we can install the two bearings on the main body, where the upper link of the suspension will pivot. Here again I am inserting a distance ring between the two bearings, so we can make firm connection while being able to rotate freely. The shock absorber goes in place at the bracket and it is secured with 30 mm M3 bolt. That completes the suspension mechanism. Next we can install the track support wheels in place. The same bracket is used for that purpose. First we need to insert an M4 nut there. Then we will use an M4 bolt as a shaft, or actually on top of it a 6 mm 3D printed shaft. As these wheels are not carrying any significant load, just supporting the upper track link's weight, they are fine with just a 3D printed shaft like this. So an M4 bolt, then goes the 6mm 3D printed shaft, then the wheel, and lastly a washer. All of this is fastened to the bracket and the nut that we previously inserted. We can repeat the same procedure for the other road wheels. Though we can notice that the front road wheel upper link is slightly modified. It has a lever that will be connected to the front idler wheel in order to provide dynamic tension for the track. To make that mechanism, here we have two additional parts that we need to connect to each other. I used a 2mm pin for that purpose, which I got it from an aluminum welding rod. These joints needs to be able to freely rotate. Now we will connect the two sides with 40mm M5 bolt. The bolt goes on the road wheel's side and a nut is placed inside the link on the idler wheel side. Then we can add two nuts in between them and screw the bolt into the idler wheel side. At the back side of the idler wheel, we need to insert an M4 nut on which the idler wheel shaft will be secured. Now we can attach this whole sub-assembly onto the main body in the suitable slots with the bearings in them. Here's how the final mechanism should look like. With the two nuts we can adjust the distance between the idler wheel and the road wheel link. Lastly, we can secure the idler wheel into the nut that we installed previously at the back side of the link. That completes this sub-assembly, and now we are able to tension the track both statically and dynamically. Actually, the whole suspension system is now done. Next, we can move on with installing the sprocket of the tank. That's the thing that actually drives the tracks or the tank, and it should be connected to the motor of the tank. The motor for this tank is a 12 volts DC motor, model 895, that has 200 watts of power and 300 RPM. As I already said, the 300 RPM is too much for this tank, so therefore we will need to build a suitable gearbox for it. So first we secure the motor to the gearbox base with 4 bolts. Then we can insert the first gear onto the motor shaft. For securing it in place, there are 2 slots in the gear where we can insert M3 nuts, and then using M3 screws we can firmly secure the gear to the motor shaft. Then we can insert the next gear to form the first gear set that makes 1.88 to 1 reduction ratio. The shaft for this gear set will be an M4 M8 threaded rod. I measured the length that I needed and cut it to size with a hacksaw. Once we have the shaft ready, first we can insert a bearing on one side of the gearbox base, and through it goes the shaft. Then a distance ring between the gear and the bearing that will provide a proper positioning of the gear, as well as avoid introduction of axial forces to the bearing, just like discussed previously. Then again a distance ring, the 17 teeth gear, again a distance ring, and a 32 teeth gear. One more distance ring and a bearing at the other side of the gearbox base. You can get the dimensions for each distance ring on the website article. Lastly, we can add M8 lock nuts on both sides of the shaft, and with that secure everything in place. This shaft is called counter shaft, and all the gears to it should be fixed to the shaft so that they rotate together with it. These gears will transfer the motion to the next shaft, which will be the output shaft, so therefore we need to tighten these gears in place with the grab screws. Make sure you tighten them as strong as possible because the motor is quite powerful. Next we can assemble the output shaft. We start with the bearing on one side, then a distance ring, and then it comes the first output or driven gear. These driven gears are inserted onto the output shaft with bearings in them, because they have to run independently from the output shaft. You see, we insert 2 bearings in this gearbox with a distance ring in between. We can notice how these gears have another set of teeth called dog teeth, which actually transfer the motion from the input gears to the output gears. You will see that how it works in a minute. Next into the shaft should go the synchronizer hub. This hub should be fixed to the shaft and should rotate together with the output shaft. That's why we insert M3 nuts into its slots and so we can tighten the hub to the shaft with some grab screws. Then it goes the shifter sleeve and the other driven gear for the second gear set. We complete the output shaft with another distance ring and 2 more bearings at the output side of the gearbox. Here we use 2 bearings because this will be the actual output to which the sprocket will be attached. In order to complete the gearbox, we need to insert in place the shift fork and shift shaft. With the help of the shift fork, we move the shifter sleeve to select one of the 2 gear sets to be active output. The shifter shaft is guided through an opening on the sides of the gearbox base, and it's connected to the shifter fork with an M3 bolt and a nut. Now the gearbox is done, and let me demonstrate how it works for those who wonder. If we rotate the input shaft, we can see how all of the gears rotate all the time. That might seem weird, but that's the trick. The driven gears rotate independently because they are connected to the output shaft through bearings. When the shifter sleeve is in the middle, the output is in neutral, and it doesn't output anything. But if we move the shifter sleeve into any of the driven gears, the dog teeth of the driven gear engage with the shifter sleeve that have the same type of teeth and transfers the motion from that driven gear to the synchronizer hub, which is connected to the output, and so the driven gear rotation is transferred to the output shaft. The dog teeth of the driven gear and the shifter sleeve are chamfered, which allows the sleeve to slide into the gears even when the gears are in motion. This is actually how a manual transmission of a car works. We can see it here one more time in action with the motor running, how the input motion is transferred to the output of the shaft. The most important thing to understand how it works is to remember that the driven gears rotate independently, and they only engage with the output when the shifter moves to the particular gear. So we can select one of the 2 different gear sets that give different speed reduction. Nevertheless, I probably spent too much time explaining the gearbox, but I think it was worth it. It's really cool how it works. Now let's continue with inserting the gearbox in place. At the back side of the tank there is an opening where the gearbox should fit in, but I have forgotten to take into consideration the nut holding the countershaft, which was popping out of it, and so the gearbox couldn't fit in. Of course I didn't want to print that main body part once again, so with the help of some drill bit and flash cutters I took out some material off of the side to make room for the nut. No worries, the 3D model files will be updated to include that opening. The gearbox now fitted in place. Finally, using some M3 bolts and nuts, we should secure the gearbox to the main body of the tank. Next, we can attach the sprocket to the output shaft. The sprocket is composed out of 3 parts, left and right teeth and a shaft coupler. The shaft coupler has slots for inserting M3 nuts in it, which are then used for securing the coupler onto the output shaft with some M3 grab screws. We need to install some M3 threaded inserts into the coupler, and then we can add the other parts in place. We complete the sprocket assembly with 3 20mm long M3 bolts. Please note here that we should properly align the teeth on both sides so that the tracks can fit on them later on. Now that the sprocket is done, we can move on and have some fun assembling the track. Yep, we're gonna have some fun assembling the tracks. Why? Well, we need 107 of these track links to form the track for the tank. The track links are designed so that they are connected to each other with just a single 2mm pin. As for a pin, I am using an aluminum welding rod with 2mm diameter. Though it could be any other material, but these are cheap and easy to get, and also easy to work with. We can just measure the length we need and using pliers cut them to size. Then, one by one, connect the track links together with the pins. The outer holes of the links are tight fit with the pin, so the pin won't be able to come out of it, but the inner holes are loose fit, so the links can rotate freely. Though, make sure you clean the track links nicely before connecting them together, because they are hard to print and might have some excess material on them. Now grab yourself a cup of coffee or something and enjoy assembling the track for a couple of hours. Once you are near the end, you should check out what exact numbers of links you will need and whether there is need for adjusting the position or the tension of the idler wheel. At the end, we simply connect the first and the last track link using the same method and we are done. The track moves quite smoothly. It's so cool to see something that you have created with that many 3D printed parts in action. Obviously, now we have to repeat the same procedure to assemble the other side. Once I had both sides done, I put the tank down on its tracks and oops, the tank dropped down completely, especially the back side. I didn't expect the coil springs to be that weak, nor the tank to be that heavy. I tried to pre-tension the coil springs by lowering the support ring to the bottom. This way the coil spring exerted more force, but still it wasn't enough to hold the tank properly. So in this situation, a solution would be to use another stronger coil springs, but I didn't have any at the time of making the tank. Though I had one more extra pair of the same coil springs, as I bought them as a package of 4 and I used only 3 per side. So I disassembled the shock absorber and added those extra coils to the back shock absorber. Now with the double coil springs and the shock absorber at the back, the tank suspension was working properly. Okay, next we can install the servo motor that actuates the gear shifter sleeve for selecting gears. I'm using a 25 kg rated digital servo here, though this one has the same size as an MG996R servo, which could also be used as an alternative. We will secure the servo first to a bracket with the help of some threaded inserts and M3 bolts. The bracket is then secured to the main body of the tank. This positions the servo at the right place to connect it to the gearbox shifter shafts. For that purpose, I 3D printed a servo horn that goes on top of the servo output shaft and 2 links that will connect to the gearbox shifter. We can use the same 2mm pins to connect them. It's a bit tight fit here, so make sure you cut the pins exactly to size. The horn is connected to the servo with an M3 bolt, and I used 2 M2 bolts for connecting the horn with the links, but you can also use anything else with 2mm diameter. Nevertheless, now let's take a look at the electronics for this RC tank and explain how it works. The brain of this RC tank is an Atmega 2560 microcontroller based board. For driving the two 200 watts DC motors, I will use 2 BTS 4960 DC motor drivers, which support PWM control and up to 43 amps of peak current. The DC motor's operating voltage is 12 volts and we will power everything with 3S LiPo battery, which gives around 12 volts. I also included a 5 volts voltage regulator, the LM350IC, in order to have a dedicated 5 volt supply for the servo motor and the WS20 at 12 bit addressable LED strips. I divided the LEDs into 3 strips, one for the front lights containing 16 LEDs and 2 strips with 3 LEDs for the back lights, and each strip is controlled with a single digital input pin. For more details how these addressable LEDs and some of the other electronics components work, you can always check my detailed tutorials about them. There will be links to each of them on the website article. The RC receiver is powered with 5 volts and communicates with the controller through the serial port. Lastly, I made a simple voltage divider which I will use for monitoring the battery voltage. Now, in order to keep the electronics components organized, I designed a custom PCB for this RC tank. The PCB will be compatible with the Atmega 2560 microcontroller based board to be directly mounted on top of it. In addition to the circuit diagram that I explained earlier, I included several more connections to this PCB to make it ready for future upgrades of the functions for this RC tank. Like for example, adding a robotic arm on top of it, or a snowblower on the front, or maybe something even cooler. So here are 3 spots for connecting stepper motor drivers, 3 connections for controlling DC motors directly from the board with transistors, 12 volts rail and 5 and 6 volts rail with digital pins connections arranged for connecting servo motors directly to them. The 6 volts rails can be powered from an external buck converter. There are also connections for an NRF24L01 transceiver in case we want to control the tank with that module, I2C connections, other digital and analog pin headers and so on. I ordered the PCB from PCBWay. Here we can simply upload the Gerber file, choose the properties of our PCB and order it at a reasonable price. I didn't change any of the default properties except for the PCB color, which I chose to be blue. You can find and download the Gerber file from the PCBWay project sharing community, through which you can also directly order this PCB. Nevertheless, after several days the PCB arrived. The quality of the PCB is great and everything is exactly the same as in the design. Assembling the PCB is pretty straightforward as everything is labeled. I started with soldering the pin headers at the bottom of the PCB for the Atmega 2560 connection and then continued with the top side. For our convenience, we should first solder the smaller components like the resistors, the transistors and the pin headers, and then the bigger ones like the capacitors, the voltage regulator and the terminal blocks. Of course, we don't have to solder every single connection on the PCB, just the ones that we will use now. Before attaching the custom PCB in place, we should first secure the Atmega 2560 board in place. There are holes in the middle of the tank where we should install some threaded inserts and secure the board to them with some M3 bolts. On the other side we can use longer bolts and nuts to match the height of the board and so secure it in place. Then the custom PCB simply goes on top of the board. Now we can connect the other components to the PCB. Here's the BTS 7960 DC motor driver, which is actually quite bulky, so I made a bracket for it to be mounted on. We use M3 bolts to secure it in place. Then according to the circuit diagram we can make the connections. The 12 volts power supply for the drivers come from the 12 volts output terminal on the PCB, and the motors are connected directly to the motors terminal on the driver. The control pins are all labeled and easy to connect to each other. Though I messed up few pin connections for the drivers on the custom PCB, but I will update the PCB so you don't have any problem with it. Next we can install the LED lights. For the front lights we need 16 LEDs and I 3D printed the LED holder with a transparent filament. The holder has a tiny slot where the LED strip goes and stays in place firmly. The LED holder outer wall has only 3 wall lines so that more light can pass through it, but that makes the LED strip more visible, which I actually didn't like how it looked. Therefore I used a diamond grid file to sand the wall and make it matte. The visual appearance is much better this way, I think. For connecting the LED strip we just need 3 wires, one is for the signal pin and 2 for the power supply. We put the LEDs in place and connect them to the 5V rail pin header together with the signal pin. In the same way we can install the LEDs at the back side of the tank. For the radio communication I am using the FlySky RC transmitter and receiver, which are really affordable and work great. For connecting the receiver to the microcontroller we can use jump wires. The receiver communicates with the microcontroller through an iBus and the serial port, so we need just 3 wires, VCC ground and the signal pin. If we want to send data back from the receiver to the transmitter, in our case for monitoring the battery voltage, we also need to connect the sensor iBus of the receiver to another serial port. Lastly, we can connect the LiPo battery. Depending on the battery, we need to have a suitable connector. This goes into the 12 volts connector and right next to it we have an on and off connector to which we will connect a switch for turning on and off the power of the platform. Please note here that before powering the board we should remove everything from the 5V rail and adjust the variable voltage of the LM350 IC to 5V using the trimmer. Now we just have to put the top covers in place. On the backside cover we attach the on-off switch and the RC receiver antennas. And so we are done with this RC tank. Honestly, I just love how it turned out. What's left to do in this video, although it's already too long now, is to take a look at the Arduino code. I will just quickly go through the code and on the website article you will be able to find more details how it works. So, using the iBus BM library, we read the incoming data from the RC transmitter. The right joystick, channels 0 and 1 are used for controlling the motion of the tank. The left rocker switch, or channel 6, for controlling the servo for shifting the gears, and the other 3 rocker switches for controlling the LEDs. We convert the incoming data into values suitable for PWM control of the DC motors, which is from 0 to 255. We send the PWM values to the drivers and the motors using the analog write function appropriately. For the servo motor and shifting the gears, we should adjust these values here according to the servo we are using. As for the lights control, we check which rocker is switched and according to it, light up each LED individually as needed. The police lights strobe effect took me some time to code it, but it came out really cool. Like I said, for more details how the code works, please check out the website article. Once we upload the code, we can power up the tank and the RC transmitter for testing it out. On the transmitter display, we can notice the LiPo battery voltage as well as the receiver and the transmitter voltage. Here first we can see how the gear shifting works in motion. With the left rocker switch, we can switch the gears while the motors are in motion. That's so cool, isn't it? With the other 3 rocker switches, we control the tank lights. There are 4 different modes. First mode, 5 LEDs on each side in white color. Second mode, all white LEDs on. Third mode, all white LEDs flashing. And of course, the coolest mode, a police light strobe effect. The tank can move with any of these light modes on. Just a quick note here though, as the LEDs are powered through the 5 volts coming from the LM350 voltage regulator, it can get quite hot, especially if all white LEDs mode is in use. Each LED consumes around 50 to 60 milliamps of current for white color, so that's almost around 1 amp of current. The LM350 can handle up to 3 amps of current, but it needs a big appropriate cooling for that purpose. I actually placed it in a wrong location on the PCBs, so I couldn't add suitable heatsink. I tried adding some small heatsinks from a stepper motor though. They helped a little bit, but still, if all white LEDs are on for a longer time, the voltage regulator would overheat. But on all other modes we are fine, so I left the things as they are. In case we want to fix this issue, we could add a separate buck converter like this with 8 amps rated current. This buck converter can be powered from the 12 volts output terminal, and its 5 or 6 output that we set can go to the 6 terminal on the PCB, and we can use the 6 volts rail for powering the LEDs. Nevertheless, I hope you enjoyed this video and learned something new. I also hope you will have fun building and driving this RC tank. Like I mentioned earlier, in future videos I plan to make some upgrades to this tank. I could add a robot arm on top of it, or maybe make a snowblower, or maybe something even cooler. So stay tuned. Don't forget to subscribe, and for more tutorials and projects, visit howtomechatronics.com.